सो आज डिस्कस करेंगे प्रोजेक्शन ऑन ए इंक्लाइन प्लेन। प्रोजेक्शन ऑन एन inclined plane. So इसका बेसिक जो हमारे पास रहेगा, दिस इज inclined plane which is having an inclination angle beta, and projectile is projected from the bottom of this inclined plane, and let us suppose it touches the point P on this inclined plane with the angle alpha to the horizontal. So this is our x-axis, and we have assumed that this is a y-axis, and this is initial velocity u, this is point O, and let us say this is point Q, or rather we can say let us this point be Q. So this will be the range of the projectile. Okay, and let me write this angle. This angle is alpha, angle of projection with respect to the x-axis in this case. So we can write it this as same thing. A particle is projected. Particle is projected from point O on the foot of the inclined plane. So in this case we can say that u is the velocity of the projection, alpha is the angle of projection, with x-axis, and beta is the angle of incline, This is the angle of incline beta. So in this case we are going to find out, so we are going to find first the range along the incline, determine range along the incline. Second, time of flight, which means time taken from point O to point P. And third, vertical height at which projectile strike. Vertical height at which projectile strikes. Okay, So first we are going to find out the range. Let's call this A part, and we say that range along the incline. So there are various methods to find out the range along the incline. So one by one we are going to discuss all these methods. So first is method 1. And let us call this figure as figure 1. So in method 1, so from the figure 1, P is the point where the projectile strikes. P is the point where the projectile strikes. So we can find out the coordinates of this point. So we can say that coordinates of point P can be written as r cos of beta and r sine of beta. Coordinates basically means this will be the x and this will be y. So in case we say that the coordinates of this are represented by x comma y. So this will be our x, this is r and cos of beta, and this will be our y. So we can say that x will be this part and y will be this part. So we are going to get coordinates as x comma y. Now we already know the equation of the trajectory of a projectile. You can see that equation of trajectory is given as y is equal to x tangent alpha minus gx square divided by 2u square cos square alpha. This is the equation, and let us call this as equation number 1. So as point P will be lying on this equation of the trajectory, point P will lie on equation 1, or we can say that the coordinates of point P are given as r cos of beta, r sine of beta will satisfy equation 1. So we are going to put these values. We are going to get this as r sine of beta is equal to r cos beta into tangent of alpha minus g r square cos square beta divided by 2u square cos square alpha. Taking cos beta common from the right side, we can write this as r sin beta is equal to cos of beta r tangent of alpha minus g r square cos beta divided by 2u square cos square alpha. Now dividing this side, we get r tangent of beta is equal to r tan alpha minus g r square cos of beta divided by 2u square cos square alpha. R and this square cancels out. Now we bring this into opposite side, so we are going to get this as tangent of alpha minus tangent of beta will be equal to gr cos of beta divided by 2u square cos square alpha. Now tangent of alpha and tangent of beta can be written as sin alpha divided by cos alpha minus sin beta divided by cos of beta is equal to g r cos of beta divided by 2u square cos square alpha. Taking LCM on the left side, we can write this as sin alpha into cos beta minus sin beta cos alpha divided by cos alpha cos beta is equal to gr cos beta divided by 2u square cos square alpha. Cos alpha and this square cancel, and sin alpha cos beta minus sin beta cos alpha will be equal to sin of alpha minus beta divided by cos beta is equal to gr cos beta divided by 2u square cos alpha. From this we now simply solve it for r. So r will be coming as 2u square sin alpha minus beta multiplied by cos alpha divided by g cos square beta. So this is the range equation as per first method. Now we are going to use second method, and in the second method we are going to change the axis. This is method 2, and in this case we are going to shift the x-axis as well as y-axis. So this is the horizontal plane, this is the inclined plane, and we are going to consider that this inclined plane is in x direction, so this will be our y direction, and rest we are going to get almost same things. This is the projectile, this is point P, this is angle beta, and this angle is alpha, and so this angle will be alpha minus beta. So in this case, and this will be our velocity of projection u, and now the acceleration due to gravity will be acting vertically downwards in this direction g. So it is going to have two components along the x-axis and perpendicular to the x-axis. So angle will be beta. So we are going to have first component, this will be g cos of beta, and this will be g sine of beta. So in this case, we can similarly write as we taking axis along the inclined plane, and perpendicular to the incline. This means that components of velocity and acceleration along the incline means x-axis, and perpendicular to the incline. Perpendicular to incline mean y-axis. So we can write ux is equal to u cos of alpha minus beta, uy will be equal to u sine of alpha minus beta, ax will equal to minus g sine of beta, and ay will be equal to minus g cos of beta. Okay, now let us call this as figure 2 rather, figure 2. So method 2 is based on figure 2. Now when the projectile lands at point P, its y component will be equal to 0. You can see that its y coordinate is 0, or in other terms we can say that s of y will be equal to 0. So we are going to use the kinematics equation that S of y is equal to u by t plus half a y t square. S of y is 0, so 0, u of y we already know is given as u sine of alpha minus beta into t minus half a of y is g cos of beta t square. So from here we can find out value of t is equal to 2u sine alpha minus beta divided by g cos of beta. This is our time of flight from O to P. This is point O. This is equal to time of flight from O to point P. Next, we find motion along the x-axis. Motion along x-axis, that is inclined plane. The kinematics formula will be equal to S of x is equal to ux t plus half ax t square, and in this case Sx will be equal to r. So if we put the values, Sx is r, so we put r is equal to ux we already know is u cos of alpha minus beta into t minus half g sine of beta and t square. Next we put the value of t in the equation. Putting the value of t in the equation, we can write that r is equal to u cos of alpha minus beta into 2u sine of alpha minus beta divided by g cos beta minus half g sine of beta 4u square sine square alpha minus beta divided by g square cos square beta. So this g cancels, this cancel out with 2, so we are left with this will be equal to 2u square cos of alpha minus beta sine of alpha minus beta divided by g cos of beta minus 2u square sine beta sine square alpha minus beta divided by g cos square beta. Now we take the common. This will be equal to 2u square sine alpha minus beta divided by g cos of beta is taken as a common, so we are left with cos of alpha minus beta minus sine beta sine of alpha minus beta divided by cos of beta. Taking the LCM, we get this as 2u square sine alpha minus beta divided by g cos beta. So we will get this as cos of beta multiplied by cos of alpha minus beta minus sine beta sine of alpha minus beta divided by cos of beta, and this will be equal to 2u square sine alpha minus beta divided by, this will become a g cos square beta and cos of beta plus alpha minus beta, and beta cancel out with beta, so the range will be coming as 2u square sine of alpha minus beta cos of alpha divided by g cos square beta. So this is the range as per method second. Now we are going to use method third. In this case, we are simply going to use the almost same diagram which was used in the method 1. So once again we are going to draw it. Projectile is projected from here and it strikes at point P. This point is given as Q, this is O, and we know that this is beta. This angle is alpha, and we take this as x-axis, this will be our y-axis, and the range, this will be our range. Let us suppose we call this as x and we call this as a y. So the coordinate system is x-axis is horizontal and y-axis is vertical. So under this condition, motion in x direction, motion in x direction, we can see that x will be equal to horizontal component rather of the velocity into time t. So we can write this as u cos of alpha into t. T we already know, we can write that x will be equal to u cos of alpha into time t, that is given as 2u sine alpha minus beta divided by g cos of beta. Now from triangle OPQ, we can write that x will be equal to r cos of beta. So from here we can write that r will be equal to x divided by cos of beta. We already know what is our x, so we put it here. We get this as 2 u square sine alpha minus beta into cos of alpha divided by g cos square beta. So this is equal to our range. Okay, now the B part, we are going to find out vertical height at what projectile strike. Vertical height at which projectile strikes. So we are going to use method 1. In this case, we are simply going to use the equation of the kinematics, which said S of y is equal to u by t plus half a by t square, and S of y is taken as y, u of y is u sine alpha, and a of y is minus g. So we put these values, we get y is equal to u sine alpha into t minus half g t square. We already know value of t, so we put in this equation y is equal to u sine alpha and t is u sine alpha minus beta divided by g cos of beta minus half g t square. So this is 2u sine alpha minus beta divided by g cos of beta and its whole square. This can be further solved as 2u square cos alpha sine beta sine alpha minus beta divided by g cos square beta. This is equal to vertical height. Now we are going to sort same thing by using method 2. In this case, we directly make use of a triangle. So we can say that in triangle OPQ, y is equal to x tangent of beta. Y is equal to x tangent of beta. So we already know value of x. So we can write that y is equal to u cos alpha multiplied by 2u sine alpha minus beta divided by g cos beta into tangent of beta. So we can solve tangent of beta as sine beta oblique cos beta. So we get y is equal to 2u square cos alpha sine beta sine of alpha minus beta divided by g cos square beta. So this is the vertical height based on method 2. And in the C part, third part, we are going to find out when the angle of projection for the maximal range. Angle of projection for maximum horizontal range. So range we already know is R is equal to 2u square sine of alpha minus beta cos of alpha divided by g cos square beta. So we can rearrange this equation as u square 2 sine alpha minus beta cos alpha divided by g cos square beta. So this is equal to 2 sine A cos B. So we can write this will be coming as u square sine of 2 alpha minus beta minus sine of beta whole divided by g cos square beta. So this R is dependent upon these factors, and R will be range will be maximum. You can say that for range, that is R, to be maximum, this angle 2 alpha minus beta should be equal to maximum. Or we can say that 2 alpha minus beta should be equal to pi by 2, or we can say that alpha is equal to pi by 4 plus beta divided by 2. So if you put these values, we get range maximum is equal to u square 1 minus sine beta divided by g cos square beta. Cos square beta can be written as 1 minus sine square beta. Here it will be 1 minus sine square beta, and 1 minus sine square beta can be expanded as 1 minus sine beta plus 1 minus sine beta into 1 plus sine beta. So it cancels out. So we get u square is equal to divided by g 1 plus sine beta. So this is our maximum range. Okay, next we will solve it if we are having the projectile is launched in the downward the inclined plane. So projection down the inclined plane, down the inclined plane. In this case, this is the inclined plane. Angle of inclined plane is alpha, and this is the projection, and we are projecting it in the downward direction. So the velocity is in this direction, that is u, and it is making an angle of theta with the horizontal, and so we can say that this angle will be alpha, and we are taking this as our x-axis, so it means this will be our y-axis. This can be drawn showing all the components of the velocity as well as acceleration due to gravity g in this way. So let us redraw with respect to, so we have having this as angle alpha. So acceleration gravity will be in g in this direction, so it is going to have two components, one here and this angle will be alpha. So first will be g cos of alpha, this will be g sin of alpha, and we have two components, velocity, one in this direction and another one is perpendicular. So this is our u, and this angle with inclined plane is alpha plus theta, here theta plus alpha. So we have two components along x-axis, this is our x-axis and this is our y-axis. So along x-axis it will be u cos of theta plus alpha, and y-axis u sin of theta plus alpha, and this is our y-axis in this direction. So we can write these components here also. Ux will be equal to u cos of theta plus alpha, uy will equal to u sin of theta plus alpha, ax will equal to g sin of alpha, and ay will be equal to minus g cos of alpha. So if t, once again, rather capital T is the time of flight from point P to O, okay, so we can write this as after time t, and please keep in mind the time of flight in the downward direction will be different than the time of flight in the upward direction, okay. After time t, the displacement in y direction, will be equal to 0, or simply we can say s of y will equal to 0. So we are using the equation s of y is equal to uy t plus half ay t square. 0 uy is u sin of theta plus alpha into t minus half g cos alpha t square, and we get time of flight as capital T is equal to 2u sin of theta plus alpha divided by g cos of alpha. And finally, we find out the range along the inclined plane. Range along the inclined plane means in downward direction, So s of x is equal to ux t plus half ax t square. Sx is capital T, sorry, r, that is range. So we can say that r is equal to u cos of theta plus alpha. We already know value of t, that is 2u sin theta plus alpha divided by g cos of alpha minus ax is positive, so we say this is positive, half g sin alpha into 2u sin theta plus alpha g cos alpha whole square. We are simply going to solve it, and range we will get this as r. R will be equal to u square g cos square alpha multiplied by sine 2 theta alpha plus sine alpha. So maximum range in the downward direction, maximum range in downward direction will be when for sine 2 theta plus alpha is equal to plus 1. Or we can say 2 theta plus alpha is equal to pi by 2, or theta will be equal to 45 minus alpha by 2. So we can find out R maximum is equal to u square 1 plus sine alpha divided by g cos square alpha. So this can be written as 1 plus sine alpha g 1 minus sine square alpha. Sine square alpha can be written as 1 minus sine alpha into 1 plus sine alpha. So we can write this as u square 1 plus sine alpha g 1 plus sine alpha into 1 minus sine alpha. 1 plus and 1 plus cancels out, so we get R maximum in downward is equal to u square g 1 minus sine alpha. So this is the range in the downward direction. So this completes the basic analysis of our motion along an inclined plane in the downward as well as upward direction. So next time we are going to discuss some of the numericals. Thank you.